Venturing into the unknown. What is a singularity? The term singularity might sound like something out of a science fiction novel, but it's a concept deeply rooted in both mathematics and physics. Let's dive into this fascinating topic. Imagine a vast, smooth ocean. The surface of this ocean is calm and predictable, much like the world of mathematics where everything follows a set of rules and patterns. The surface represents the world of mathematics. Here, equations and functions behave in a predictable manner, allowing us to understand and navigate through various problems and solutions. Now picture a sudden, dramatic whirlpool. This whirlpool disrupts the calm surface, creating chaos and unpredictability. This is a singularity, a point where the smooth surface breaks down. In mathematics, this is where our usual rules no longer apply, and things become infinitely complex. In mathematics, a singularity is a point where a function misbehaves. It's a point where the function's value becomes undefined or infinite, causing a breakdown in the system. It's like trying to divide by zero on your calculator. You get an error message. The calculator can't handle the operation, just as mathematical functions can't handle singularities. The function becomes undefined, spiraling into infinity. This infinite behavior is what makes singularities so intriguing and challenging to understand. Singularities aren't just mathematical curiosities. They have real-world implications and appear in various fields of study. They pop up in physics too, like at the center of a black hole. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. These points of infinite density challenge our understanding of the universe. The singularity at the center of a black hole is a place where our current laws of physics break down. Understanding singularities is about exploring the boundaries of our knowledge. Scientists and mathematicians are constantly working to understand these points of infinite complexity. It's about peering into the abyss and asking, what happens here? What lies beyond the edge of our current understanding? Singularity represents the frontier of human knowledge, a place where we must venture to uncover the mysteries of the universe. As we continue to explore singularities, we push the limits of science and mathematics, seeking to understand the very fabric of reality itself. The journey is complex, but the potential discoveries are boundless. So the next time you hear the term singularity, remember that it's not just a mathematical oddity or a sci-fi concept. It's a profound and essential part of our quest to understand the universe. Whether in a classroom or a research lab, the study of singularities continues to inspire and challenge us, driving us to explore the unknown and expand the horizons of human knowledge. So, let's keep asking questions, keep exploring, and keep venturing into the unknown. The singularity awaits. The cosine function, denoted as cos x, is like a rhythmic wave that oscillates between 1 and -1. Imagine a pendulum swinging back and forth. Its motion can be described by the cosine function. The x-axis represents the angle, and the y-axis represents the cosine value. The peaks of the wave touch 1, while the troughs reach -1. This wave pattern repeats infinitely in both directions. The cosine function is essential in trigonometry, helping us understand relationships between angles and sides in triangles. It's also used in physics, engineering, and even music. From describing sound waves to modeling planetary orbits, the cosine function is a fundamental tool for understanding our world. Now, let's introduce the concept of 1 over cos x, which is the reciprocal of the cosine function. This is where things get interesting and potentially singular. Remember those points where the cosine wave touches 0? At those specific angles, 1 over cos x becomes 1 over 0, which is undefined. This is where our smooth mathematical ocean forms a whirlpool, a singularity. These singularities occur periodically along the x-axis, wherever cos x equals 0. As we approach these points, the value of 1 over cos x explodes towards positive or negative infinity. These points of singularity are crucial for understanding the behavior of 1 over cos x. They tell us where the function breaks down and becomes unpredictable. Section 4. Navigating the abyss. Different types of singularities. In this section, we will delve into the fascinating world of singularities, exploring their various forms and the implications they have in mathematics. Not all singularities are created equal. They can be as diverse as the equations they inhabit, each with unique characteristics and challenges. Just like whirlpools can vary in size and intensity, singularities come in different types. Some are mild and manageable, while others are intense and complex, requiring deeper understanding and sophisticated techniques to handle. One important distinction is between removable and non-removable singularities. This classification helps mathematicians decide the best approach to tackle these anomalies. Removable singularities are like tiny bumps on the mathematical road. We can smooth them over. These are points where a function is not defined, but we can redefine it to make the function continuous. Non-removable singularities are more like bottomless pits. They represent points where the function breaks down completely, and no amount of redefinition can make the function continuous at that point. They represent a fundamental breakdown of the function, and we can't simply ignore them. These singularities often require more advanced mathematical tools and concepts to understand and work with. Understanding the type of singularity helps us determine how to handle it mathematically. This knowledge is crucial for mathematicians and scientists as they navigate complex equations and models. It's like knowing whether we need a small patch or a complete detour. Removable singularities might just need a minor adjustment, while non-removable ones could require a completely different approach or even a new framework. By classifying singularities, we gain deeper insights into the behavior of functions and the nature of the mathematical landscape. This classification not only aids in solving equations but also enhances our understanding of the underlying principles governing mathematical phenomena. Throughout history, mathematicians have grappled with singularities, from the early pioneers who first identified these anomalies to modern-day researchers who continue to explore their depths. Each discovery has added a new layer of understanding to the rich tapestry of mathematics. Singularities are not just confined to pure mathematics. They also appear in physics, particularly in the study of black holes and the fabric of the universe. Understanding mathematical singularities can provide insights into these physical phenomena, bridging the gap between abstract theory and tangible reality. The study of singularities is a collaborative effort involving the collective wisdom and creativity of mathematicians, physicists, and other scientists. Together, they push the boundaries of knowledge, uncovering new truths and solving complex problems. As we continue to explore the different types of singularities, we not only enhance our mathematical toolkit but also deepen our appreciation for the intricate and beautiful world of mathematics. The journey through singularities is challenging, but it is also incredibly rewarding, offering endless opportunities for discovery and innovation. Section 5, a calculated plunge, solving a cosine singularity problem. In this section, we will delve into the intriguing world of singularities, specifically focusing on the cosine function and its peculiar behavior at certain points. Let's dive into an example to see how we handle cosine singularities in practice. Understanding these singularities is crucial for anyone studying advanced mathematics or physics, as they often appear in various complex problems. Suppose we want to find the limit of 1 over cosine of x as x approaches pi over 2. This is a classic problem that illustrates the concept of singularities in a clear and concise manner. First, we recognize that cosine of pi over 2 equals 0. This is a fundamental property of the cosine function, and it sets the stage for the singularity we are about to explore. This means we're dealing with a potential singularity. A singularity occurs when a function takes on an infinite value or becomes undefined at a particular point. But what kind of singularity is it? Singularities can be classified into different types, such as removable, non-removable, and essential. Understanding the type of singularity helps us determine the behavior of the function near that point. As x gets closer and closer to pi over 2, the value of cosine of x approaches 0. This gradual approach to 0 is what creates the singularity in the function 1 over cosine of x. While 1 over cosine of x shoots towards infinity, this dramatic increase towards infinity is a hallmark of a non-removable singularity, indicating that the function cannot be redefined to make it continuous at that point. This indicates a non-removable singularity. Non-removable singularities are significant because they represent points where the function's behavior becomes extremely erratic and unpredictable. Therefore, the limit of 1 over cosine of x as x approaches pi over 2 does not exist. This conclusion is crucial for understanding the limitations and boundaries of mathematical functions. The function becomes unbounded, spiraling into the abyss of infinity. This unbounded behavior is a key characteristic of functions with non-removable singularities, and it has important implications in various fields of study. This example demonstrates how understanding singularities helps us analyze the behavior of functions. By studying these points of infinite value or undefined behavior, we gain deeper insights into the nature of mathematical functions and their applications, even when they become undefined at specific points. Singularities are not just abstract concepts, they have real-world applications in physics, engineering, and other sciences. By mastering the analysis of singularities, we equip ourselves with powerful tools to tackle complex problems in various domains. Section 6. The significance of singularities. Understanding the universe's secrets. Singularities might seem like abstract mathematical concepts, but they have profound implications for our understanding of the universe. In physics, singularities appear in Einstein's theory of general relativity, which describes gravity as the curvature of spacetime. Black holes, for instance, are thought to contain singularities at their centers. These points of infinite density challenge our current understanding of physics. They suggest that our current theories are incomplete, and that new physics might be needed to describe what happens at these extreme scales. By studying singularities, we're not just exploring the boundaries of mathematics, we're pushing the limits of our knowledge about the universe itself.